name is Maxim, and I'm the team leader of the data integration team in Exness. And with me, Ilya here. Ilya is data engineer, and we work on different data integration stuff, and not only, and also on services on data. And firstly, let me ask you, please raise your hand who have started using Flink already. Some of you, at least one. Only one? Okay, guys, I know you do it. Okay, okay, I see some hands. That's great. So maybe some of you just thinking to start using Flink. Raise your hand. Okay, okay, okay. 2 more hands. Nice. So, by the way, I hope this presentation will be useful for you. Okay, and in the first part, we will talk about introduction of Flink at Exness. And in the second part, Ilya will highlight some Flink fundamentals, so you could get more familiar with it. Several years ago, we introduced Kafka. And I think all of you know that Kafka is a message broker and widely used. And since then, our stack varies, but Kafka remains an integral part of it. And after a few years, we introduced Kafka Connect as our main service for data integrations on streams. And with Kafka Connect, you can easily load data to Kafka and then from Kafka. And in 2020, we understood that we need some stateful stream processing on Kafka. And we tried Flink for the first time. And we tried it for some stateful integration, basically, yes, again, integrations. And since all this time, and all the time, basically, Exness has been growing. And the amount of data was always growing with Exness. And we felt some high demand on stream processing in our company. And we wanted to try like Flink again or some another solution which will be well implemented, because our first implementation of Flink had some severe problems and we couldn't really appreciate its full potential. All right, so why did we needed stream processing in general? First of all, as I mentioned, the amount of data was always growing. And some of our traditional approaches like batch processing was not enough. And even if you run it every minute, it just couldn't work with such amount of data. And also, everyone asked us to reduce latency in our data streams, in our data pipelines, in our services, everywhere. And also, as a team, we needed some modern and well-implemented solution for data integration purposes. And also, other teams in technology in our company asked us to provide them with some solution, some system to make them able to apply their own algorithms on streams. And what is stream processing in general? And there are, you can see some cases for stream processing, and some of them like fraud detection. You can see it here. So you can see some stream processing examples. For example, fraud detection, log analytics, stream analytics, and machine learning prediction. And when you're talking about streams and stream processing, you always think about 2 main things, 2 main metrics. Latency, that you always need to decrease, and throughput, that you always need to increase. And on the schema below, you can see some example of stream processing application. And let's imagine we have some customer, and it uses our web application. And this web application collects some data like cookies, fingerprints, clickstream, or whatever, some information about our customer. And then this application then sends this data to our fraud detection system through Kafka. And this fraud detection system is basically some stream processing solution. So it reacts on these messages almost in real time once they appeared. And It calculates some scores, makes some predictions, enriches data, or does whatever, basically. And then it returns data back to Kafka, and then our web application could use it to make some decisions based on this data. For example, this web application could hide some specific pages for this particular customer, or vice versa, to show some pages. All right, and what is streaming job in general? So first of all, it's a microservice. And the main idea that the input and the output is the same. And if you want to build some complex, sophisticated solutions, you can just combine these microservices in one big and branched chain and implement some really not hard, but complex algorithms on streams. And also here you can see that then this data could be used by services or could be stored to data lake or data warehouse or used somehow differently. Okay, so how did we choose Flink? In the beginning of 2022, in the first quarter, we wanted to try something simple, much more simple than Flink. And we tried KSQLDB. It's some kind of extension of Kafka, and you also could make some computations on streams. And you also can make it stateful. So you can store some state and use it within the job. But the main problem with this solution that you cannot use different Kafka instances with one KSQLDB. And so in our company, we have a lot of Kafka instances, so we needed something more complex. So after our first try, in the second quarter, we wanted to, as I said, like some more modern, well-implemented, and we started some comparison of different stream processing solutions. And we started as simple as we could. We just collected all the features of different solutions in one big table and tried to compare just by documentation. And after this research, we understood that only two solutions are more suitable for us. And it was Flink and Spark Streaming. And we decided to focus on them more. We not only compared by documentation, so we started to implement some real business cases. So some first POC, or proof of concept. And firstly, we implemented very poorly, just like to try and to compare. And after this first implementation of the same solutions on Flink and on Spark Streaming, we decided that Flink is much more better and more suitable for us. And then in the third quarter and further, we started to implement some real business cases for our customers within our company. And this year, we're trying to implement self-service. So we want to provide self-service for teams in technology, so in technology department. And so we hope that we will do it soon. Why Flink in general? So it's Java-based, and our main expertise is in Java, so we can easily develop it, extend if we need. It's open source, so we don't need to pay for it. It has native Kubernetes support, and you can easily deploy it on our on-prem cluster. So we use on-prem clusters, so it's really important for us. And also, as I said, we previously had some Flink experience, and we wanted just to extend this experience and apply it to our new solution. And you can ask, why not Spark Streaming? And after this POC, we understood that Flink is slightly more convenient to use, and it looks easier, and it has better documentation. And Flink, it's a pure stream processing solution. And Spark Streaming, these times, operated with micro-batching. And it means that you, like Spark streaming, needs to accumulate some data before processing it. And in our cases, we needed some really low latency. Some of our applications has latency less than 20 milliseconds. So we really needed something very fast and not something like micro-batching. And also, we found some features that in Flink that we couldn't find in Spark streaming. And there is some of the main features of Flink. So first of all, it's stateful processing. So you can accumulate some state, aggregate some state, and then use it between or in different jobs, yes. And also, you can use different times. So you can use processing time and event time. And Ilya will highlight this in the second part of presentation. Also, you can use checkpointing. So if your job is failed, you can easily restore it from some checkpoint and continue processing your data. Also, Flink provides different layers of API. So you can, if you want to speed up your development, you can use Flink SQL. And if you want to have more tuning, more precise tuning with like some magic, you can just use DataStream API, which is basically Java API. And also, the last one is my favorite, that you can combine streaming jobs and batch jobs together. Basically, not jobs, but tasks within the same job. And for example, you want to read historical data from some database and then continue processing only the new data within the same job. So on Flink, you can do it pretty easy. And there are some examples of use cases at Exness. Basically, you can split these examples only in two categories. Some stateless or stateful processing with enrichments from external systems. And we have some jobs where we enrich our streams from API or from database. And the second one is stateless or stateful processing without enrichments from external systems. And we use it in our aggregates on streams. So we calculate some aggregates for 1 month and for 1 day. All right. So that's it for me. Yes, that's it for me. And I give the floor to Ilya. Thank you.
Hello, everyone. My name is Ilya. I'm a data engineer here at Exness. And it's actually good that none of you have worked with Flink, because in the second part, we will briefly go over the main building blocks of a Flink cluster. We will look at basic attributes of a streaming app, and we will look at 3 use cases of using Flink at Exness. A Flink program is actually a graph of tasks, some of which can be run in parallel. And to do so, Flink cluster has 3 main components: a client, a job manager, and 1 or more task managers. A client is not a part of the job runtime. Rather, it is used to submit a job to the it is used to prepare and submit a job graph to the job manager, and then it can disconnect or it can stay connected to receive progress reports. Job manager manages execution of jobs, triggers checkpoints, sends heartbeats, and updates job statistics. And the task manager is the actual worker. It runs computations on incoming data, and it exchanges data between tasks on different task managers. Each task manager is a separate JVM, and it can execute 1 or more tasks in separate threads. Tasks from different jobs can be run on the same task manager. And of course, if you have 1 faulty task, in the worst case scenario, it can kill the whole task manager, and all the other tasks running on it will be obviously killed. To control how many tasks a task manager accepts, it has so-called task slots. And each task slot represents a fixed amount of resources on that task manager. An important concept in streaming is notions of time. And Flink supports 2 notions of time: processing time and event time. Processing time is the system time on the machines that your operators are being run on. So if you use time-dependent APIs like windows or interval joins, they will use the system time. This approach provides the best performance and lowest latency, but it won't provide determinism. And that is because your incoming data can come at different speed to different task managers, or your wall clock on your machines can be simply out of sync slightly. And to solve these problems, Flink introduces event time. And event time is generally the time at which an event was generated on its producing device. So the time is embedded within records before they enter Flink. And you have to tell Flink how to parse those timestamps. So when you use event time, the question is, how do your operators know what time it is? And to solve this problem, Flink introduces watermarks. And watermarks is a mechanism to measure progress. So watermarks flow as a part of your stream, and they carry a timestamp t. And watermark at t declares that there should be no more events coming in the stream with a timestamp less or equal than t. And now that we know the basics, let's take a look at Flink APIs, like a bird's eye view. So Flink has three main APIs: DataStream API, Table API, and SQL. DataStream is the original API. It is imperative API. It's very flexible, but requires a bit steeper learning curve compared to the other ones. So basically, you use the DataStream class to describe your collection of data, and your initial data stream will be created by adding a source in your Flink program, and all the subsequent streams will be derived by combining this original one with Flink APIs, like map, filter, and etc. Table API is a higher level API. It's more declarative. It looks very similar to Spark SQL. So you intuitively compose your query by using statements like select, filter, join, union, and etc. It's a unified API for both batch and streaming. And you can actually combine Table API, SQL API, and DataStream API within one Flink job. Okay. And now let's take a look at the jobs that we run at Exness. We actually just have two types of jobs. We have Java jobs and Flink SQL jobs. For Java, we just we have one repo per job, and they all use DataStream API. And we also have like a shared library of Flink utils with a bunch of utility functions that are used across all the jobs. And for SQL jobs, we have one jar, Flink SQL Runner. And this jar, it accepts your SQL query. It accepts arguments, because it knows how to substitute those arguments inside of your SQL. And it also contains a bunch of UDFs, user-defined functions, to use in your SQL if you need to. And now let's take a look at three use cases that we have. We have actually more than three, but all the other ones are similar. So we will take a look at this. And the first use case is to find the first trade time for each Exness user. And as inputs, we have Kafka topics with the trades coming from MetaTrader 4 and MetaTrader 5, but they don't contain all the historical trades. And we need them. And luckily, we have the dump of all the trades in ClickHouse. And because we can combine batch jobs and streaming jobs in the same query, we just do that. And we get the first timestamp. And we do that through a UDF. And this UDF, it uses Redis to cache. Basically, it keeps the state for each user in Redis, and it updates the first timestamp as the records pass through. And the second use case is calculating total trading volume for each day. And we have the same inputs as in the previous job, but we also have to consider things like social trading, abuse deals, and deals made by service accounts. And we need those because we need to substitute them from the total trading volume. So service accounts are kept in Vertica, so we need a way to pull them into our streaming app, and we need them to be fresh. So we have a UDF that will go to Vertica and just pull the fresh dictionary every 100 minutes or so. And then we deduplicate the trades, and we just sum daily. And the final job is the AntiFraud job. And in this job, we have three main components. It's sign-up events, blacklist updates, and business logic that will assign each event a score, like a fraud score from 0 to 100. And so we union all the events, all the sign-up events, and then we connect this stream with the stream of blacklist updates. And now these two streams can share the same state. And we keep all the blacklists on the Java heap because those are relatively small lists. And we run business logic through the coming events. And once we know the score, we send it to a different service. And we use async EOR API for that. And async EOR is a special API in Flink that allows you to make non-blocking requests to internal systems. And as you can see, we use both DataStream API and Table API. But when would you use one over the other? We found that it makes more sense to use DataStream API when you have to deal with late events. And late events, if you remember when we talked about watermarks, what happens if you have if you have an event with a lower watermark, lower timestamp than the previous watermark. So in DataStream API, you can control what your functions will do in that case. In Table API, not so much. Also, if you have to use lower level APIs, you have to go with the data stream. And if you want to set timers in your code or expose custom metrics. On the other hand, if you find it easy to express your job in SQL, and it's OK for you to ignore late events, you can go with Table API or SQL API, and your delivery time should be a bit quicker. And for the future plans, we are going to get more experience with Flink and try to solve more business cases at Exness. We also plan to support Python because currently we don't. We plan to drag more teams into it. Currently, we have big interest from the payments team and from the AntiFraud team. And for example, in AntiFraud, people want to be able to just drag and drop business logic and launch a job themselves. They don't want to have a developer working full-time on these things. And to solve this, we are going to try NAS-Necker, which is precisely that. It's a graphic user interface for Flink, but not only for Flink, but for Flink as well, that allows you to drag and drop business logic. And we want to introduce Zeppelin, and it's like a Jupyter notebook thing for Spark and Flink, just for people to be able to kind of play with Flink. And for the self-service, we plan to have teams create a ticket in service desk and get their Flink cluster in a matter of days inside their Kubernetes. And currently it takes much longer than that. So thank you very much for coming here.
Thank you for presentation. I have a question. In your presentation, I saw the difference between process time and event time. Then it's process time. It's something a little bit worse because it's come to server with latency. But event time could be sent from user device with incorrect time zone. And what kind of time you use and how you resolve these time zone problems. Thank you.
You're right, but basically you mentioned the problem of data. And if you have the wrong data, there is nothing you can do about it. Timestamps are just, if you have the wrong timestamp, there is nothing we can do. We use event time in a couple of jobs. Most of the times, for example, trading volume, it doesn't require any time because you just well, yeah, it does require time for the day, but it's it doesn't make a big difference in like monthly or daily trading volume. It doesn't matter. For other stuff like AntiFraud, we don't use time at all because you don't need it.
So the second question, you mentioned the Redis cache on the first. So is it kind of automatic?
No, it's completely like it's our own Redis. It's not embedded within Flink, and we could use Flink's internal because it has. We didn't talk about it here, but it can have a cache in RocksDB. The reason we don't use it is because we want to build services on top of the Redis. Basically, we want other teams to access Redis, and it's much easier to have in this particular job. It's much easier to have your state outside than to have it inside.
So, and how do you behave if something fails, like Redis, for example?
We will retry as long as possible, but yeah, it will at some point if you have a really long. Like for example, if it's not available for an hour, you will have a back pressure in your stream. So back pressure is like another Flink concept.
But what's your design if the Redis is completely failed?
It will stop working. It's.
But how you restart?
You just restart Redis.
So from the scratch?
Not completely from scratch. So the batch job that reads data from ClickHouse, it will not run again. But all the offsets that, so Flink will, it has a mechanism of checkpointing, and we do checkpoints, I think, every 5 minutes or something like that. So if your job failed, it will restart from the previous checkpoint. But it will not rerun the whole ClickHouse thing. It will only read from topics.
I'm wondering, why is it crucial for you to have your Flink be installed on premises? Is it for some security, cost, or performance reasons?
Thank you for your question. It's because we have so many teams that it's going to be unbearable for us to control like 20 or 30 Flink jobs. So that's one thing. And another thing, sometimes you want your job to be on its own separate cluster because, for example, with AntiFraud, you don't want like other jobs that run on the same task managers to have any kind of impact on your job. So sometimes you want to be completely separate installation of Flink. And we just basically, like in every big company, you want to move to self-service because otherwise you just have everything centralized and it makes things impossible to control and scale properly.
No, I rather mean, why don't you use some cloud-managed solution for Flink, or isn't it available on the market?
Yeah.
Basically, yes, we have some rules that we try to keep all our infrastructure on our servers. And we have a lot of data, and we always move this data through network, yes, and it costs a lot. And yeah, the main reason that we'll have like everything to have Flink inside. So we just don't need to use some cloud providers.
Yeah, and the consequent question then, so you have three parts of this chain. So first your MT4, MT5 trade servers, I guess probably located in London or maybe not. And you have Kafka, you have Flink. Are they located somewhere close to each other? So yeah, that was my next question. How do you mitigate, how do you solve some network-related problems when you are streaming the data?
Basically, we have MetaTrader everywhere around the world, but our main infrastructure in one place. So and our Kafka that we use also at the same place. And so we try to replicate all the data we need to this Kafka cluster and then use it within one data center.
And the Flink is also located in the same data center, so it
yes,
doesn't.
Yes. I wanted to add that basically it's not in this particular flow. It's not that important to have low latency, and even we can consume data from other locations, and it would be okay. But for some anti-fraud cases, for example, it's impossible to have some network latency. So we try to make it as closer as possible. And our applications that send data to Kafka also located at the same place as Flink cluster.
Okay, thanks a lot.
More of a generic question on my side. So when adopting a new technology, and one of the criteria is to consider the market, where it stands. So obviously Spark streaming would be a winner here. The question is, how do you estimate onboarding the learning curve for Flink for guys who have background with Spark streaming?
Basically, as I mentioned, we already had some expertise. So we tried to use this expertise. And even before we started with the last implementation, we had one of the same data engineers that were implementing the first Flink. And in general, like when we started, we almost had the full headcount, and we just find a couple of guys, basically Ilya and some other, who had some experience with Flink, so we just could apply their knowledge.
And also Spark comes from the batch world, and it had the APIs tailored to the batch needs. For example, until recently, it only had micro-batching, which it's not good for a lot of cases. And another thing is in Flink, if it doesn't matter how complicated your business logic is, you can solve it 100%, because in the worst case scenario, like you can set timers yourself in your Flink job, you can have access to RocksDB state. Like it's very low level. You can go really low level with Flink, but with the Spark streaming, not so much.